You're trying to determine if a series converges or not, and you're struggling to figure that out. Well, fret not. You've come to the right place. Today, we'll go over 9 of the main series tests, their conditions, and how they're used. Let's start with the most basic one, and the one that will build our series intuition. The nth term test has conditions so simple, it's in the name. If the nth term isn't 0, then the series diverges. Or, written mathematically, if the limit of a of n as n approaches infinity isn't 0, then the series diverges. This is a divergence test, so it's impossible to use the nth term test to prove convergence. The limit approaching 0 doesn't necessarily imply convergence, and we'll see that in many examples later down the line. Almost any series can be used for the nth term test, but let's take this one. We take the limit as n approaches infinity and see it's not 0. Thus, the series diverges by nth term test. The logic behind this test will be discussed later down the line, so let's move on. The geometric series test is next up, and although it may not be a test, for all intents and purposes, it will be here. But first, a quick primer on geometric sequences. A geometric sequence is a sequence where every subsequent term is multiplied by a common ratio, r. So if the first term is a, then the second will be a times r, the third will be ar squared, and so on. Doing some Gaussian trickery on this series can help us determine the sum of a geometric series. But does it converge or not? We notice that the r term is very important to determine that, as it's in the base of the exponent. If r is greater than 1, then the series sum approaches infinity, and if it's less than -1, it also diverges. So that sweet spot in the middle is where the series converges, as the r to the n term approaches 0. This can give us the sum of a convergent geometric series, which is s equals a over 1 minus r, and also the geometric series test. This test states that if we have a geometric series with the absolute value of r being less than 1, then the series converges, and vice versa for diverging. The diverging series of this test can also be proven by nth term test, so the convergence part of this test is the most helpful. The next test is a little interesting, as it involves becoming a pirate. That's no joke, as it's the telescoping series test. Telescoping series are only used in specific cases, so let's illustrate one example before becoming very general. 1 over n minus 1 over n plus 1 is a good example. Let's write out the sum of the series, writing only the first few terms to see if we notice anything. We notice that all of the middle terms are canceling out as we continue going down the line. This continual cancellation leaves us only with the first and last term. Telescoping series are in the form bn minus bn plus 1, or something similar, which allows this continual cancellation. Their sums are just the uncancelled terms. We know if a telescoping series converges if the last uncancelled term of the series approaches a finite number. Telescoping series are often difficult to find, but if you notice any partial fractions, logarithms, or plus ones, you should definitely take an extra look. Now, our next two tests can be grouped together, as we introduce a new way to visualize series. Series are the sums of an infinite number of terms, so could we possibly use an integral to determine convergence? It makes sense, as integrals are accumulations of change and series are the accumulation of terms, so we can visualize this better by graphing the value of a of n versus n. If we plot for, say, 1 over n, we get this graph. Now, if we want to visualize the sum of each term in the series, we can make a bunch of rectangles. These rectangles have width 1 and height a of n. This area is the sum of the series, and it can be roughly estimated with the integral. Now, the only way that this comparison can work, however, is only if a few conditions are met. The function first has to be integrable, which requires continuity. It also needs to be positive, so the integral isn't negative. And finally, to make the integral comparable to the series sum, the function has to be decreasing. So now that we have these conditions, what's the test? It states that if the improper integral of the function converges, then the series converges, and vice versa for diverging series. We can use the integral test to then discuss the p-series. P-series are in this form, or 1 over n to the p. We can do the integral test to figure out what p-values lead to convergence, and we quickly notice that if p is greater than 1, then the series converges, and vice versa. The integral test is very powerful, generally, being used in any series that meets its conditions. However, the difficulties in seeing if conditions are met and integrating are often very difficult, which is why we still have 4 more tests to discuss. Our next 2 series tests are all about comparison. To use either test, however, you need to prove the convergence or divergence of another series using another one of our previous tests beforehand. So let's start with the direct comparison test. It takes advantage of a relatively intuitive idea. That idea being, if a series is larger than a diverging series, it diverges, and if a series is smaller than a converging series, it converges. This idea can be explained with area. Converging series have a finite area, so a series that's less than it will have a lower area that's also always finite. Diverging series have an infinite area, so a series greater than it will also only have an infinite area. Another important condition is that both of the series have to only have positive terms, to prevent the area subtracting debacle that we experienced with the integral test. So, putting all of that together, we can get the direct comparison test, which is as follows. The best example for how this test is useful is the natural log of n over n. We can compare it to 1 over n, which diverges by p-series. ln n is always greater than or equal to 1 for our interval, so likewise, the natural log of n over n series is greater than 1 over n. As all terms are positive, by direct comparison test, it diverges. Limit comparison test is next. We can explain limit comparison by understanding that a convergent series times any finite number still converges, while multiplying any divergent series by any finite number causes the function to diverge. So, if we can multiply a known series by a finite number to get another series, we can prove convergence or divergence. We can simplify this expression by realizing that series largely boil down to their nth term, so we can write limits instead of summations. We can then do some algebra, and now we got the basis of the limit comparison test. If the limit of b of n over a of n approaches a finite number, we can then conclude that b of n converges or diverges, depending on a of n. Like direct comparison, all of the terms have to be non-negative, with a of n not equaling 0 to prevent indeterminate limits. Almost all of these series tests require our terms to be non-negative, so our options for what we can use are greatly limited. This is where our final 2 series tests come to their rescue. Let's first introduce the alternating series test. But first, what's an alternating series? An alternating series alternates in sign with every consecutive term. So, cosine of x isn't alternating, but cosine pi of x is. So, to understand the alternating series test, let's turn to another visual explanation, but this time with just a number line. Let's just take the series -1 to the n times 1 over n. We'll gradually write out the partial sums, or the sums of all the terms up to a certain value, indicated by the subscript. You notice that as we continually add terms, the partial sums repeatedly increase and decrease until they converge on a point. So that's how alternating series converge, but there are some conditions. In order to allow this convergence, the absolute value of the terms need to be decreasing. This is to allow the partial sums to zone in on a point, instead of just escaping it. These terms also need to approach 0, so we aren't just left with an oscillating partial sum that would diverge. So, the alternating series test will say that a decreasing alternating series will converge if the limit of a of n as n approaches infinity is 0. Additionally, if we wanted to approximate an alternating series using a partial sum, the error bound would just be the absolute value of the next term. It's understandable because when we see a convergent alternating series, the biggest jumps in partial sums, and likewise series sums, occur in the next term. Double additionally, series whose alternating form converge, whereas its normal form diverge, are called conditionally convergent, and series that converge in both cases are absolutely convergent. The final series test we will talk about is the ratio test. The ratio test is the most versatile of all of the series tests, and it functions off of a simple principle. If the absolute value of the ratio of the n plus 1th term to the nth term is greater than 1, it diverges, and if it's less than 1, it converges. It's inconclusive if the ratio is 1. This makes sense, as if a series continuously decreases, then it should converge, and vice versa. This simple test can be expanded massively to help find the convergence or divergence of almost any series. Now, I hope that these 9 tests can greatly help you on your journey to find the convergence of any series. Series are incredibly valuable in simplifying complex behaviors, and they're also helpful in getting a 5 in AP Calc PC. I hope you enjoyed this video, and goodbye.